When we look at the relative intensities of photoemission peaks from platinum, say, we see that there is a variation in intensity as a function of the photoemission peak. And this is due mostly to the physics of the photoionization of electrons from atoms within a sample by a photon of a given energy. The fact that the physics tells us we should have different intensities ought to allow us to quantify the different amounts of platinum based on any of these peaks. However, when we actually try to do this, we find that the spectrum, when measured, does not produce peaks in the proportions that we expect based on the photoionization cross-sections. The photoionization cross-sections are an important part of understanding the relative intensity of these peaks, but the instrumentation will also influence the relative intensity of these peaks. If we have an electron of a given energy that is passed through the instrument and onto the detectors, then the probability that that electron is detected changes as a function of the kinetic energy. And we talk about the transmission function of an instrument that changes with energy, and that's because the lens, column, the apertures all behave slightly differently at different kinetic energies. Now, in addition to the instrumental factors, we also have sample factors, and the sample will alter depending on the kinetic energy too. Now, what does that mean? That means that the sample which is available to XPS will alter as a function of the kinetic energy. The depth within a sample from which electrons can escape without losing energy varies as a function of the kinetic energy. So even if the instrument was perfect and the cross-sections were known, the escape depth would also have a bearing on the intensity of each and every one of these photoelectron peaks. Of all these considerations when we perform quantification, the most important is arguably the escape depth. And the reason that I say this is because XPS is a surface sensitive technique precisely because of the influence of escape depth on electrons leaving the surface. However, escape depth does have implications for the spectra that we measure. And to demonstrate how escape depth influences spectra, I'm going to make use of a data set that is measured from platinum. It's a metallic plate that has contamination on the surface. And by manipulating spectra, I can illustrate some of the influences of escape depth on XPS data. I'm going to illustrate some of the implications of escape depth to XPS by a data set that has been measured from a platinum plate that has been exposed to air. The fact that it has been exposed to air means that there's adventitious material on the surface, and we see this in the form of carbon in this particular spectrum. And if we look at the oxygen 1s, this is the oxygen 1s that is also characteristic of a material at the surface. And I know this because if the surface is sputtered with the helium gun, which is how this data set has been prepared, that with each sputter cycle we see the oxygen diminishes, and similarly we can see the carbon also diminishes with each sputter cycle. So that implies the carbon and the oxygen are at the surface, and also that the platinum is potentially below the surface of this contamination layer. And that's entirely consistent with the sample. If we now look at a survey measurement that was measured from the surface, the as received surface before sputtering, then we also see evidence of a surface contamination layer. So there's the carbon 1s, and there is the oxygen 1s. We see the oxygen Auger and also the carbon Auger peaks here. And we can see that this is very different from the surface after sputtering for over 1,000 seconds with this helium ion gun. If I overlay these two, you see this as received surface has the contamination, and more importantly we can see that before sputtering there's very little evidence of any of the structure we see here, and this structure represents Auger signal from platinum, and we don't see that because of the overlayer, and that is a consequence of escape depth, because the overlay is sufficiently thick that all signal from the platinum is attenuated and we only see a carbon Auger peak. There may be some carbon here, only as much as we can recognize it in the carbon 1s, but it's very little, and now we see all Auger from the platinum. Just verify this by the element library. Oxygen, carbon and platinum. So there we see at the surface the oxygen Auger and the carbon Auger, but after sputtering we see almost no carbon and oxygen, and we only now see Auger that was previously hidden by the overlayer. So this is a prime example of how signal is attenuated by inelastic scattering. That is the reason why XPS is a surface sensitive technique. We only measure signal from about 3 attenuation lengths into the surface, and the attenuation length changes as a function of kinetic energy. In summary, this exercise demonstrates the importance of understanding the role of an overlayer on quantification results by XPS. If we want to look at platinum in the as received surface, we have to use high kinetic energy electrons, and that's because when we go all the way down to these Auger electrons that are at a low kinetic energy, well, they disappear. You can't see them. The attenuation length is now short, and most of the signal is coming from within the contamination layer, and we don't see the substrate of platinum. So if we want to do quantification by XPS, it's in our interest to choose photoemission peaks that are close in kinetic energy. That will minimize the influence of the attenuation of signal by an overlayer.